So it's a pleasure to introduce to Habib Khosroshahi. Habib is the director of INO, the Iranian National Observatory. He was visiting us at least one time before, but he never saw us officially in an official seminar.
I think it was.
Okay.
Exactly 4 years ago, I think.
4 years ago. Okay, fine. So Habib is an expert in galaxy clusters and especially dynamics and especially galaxy groups also. And today he's going to speak about his favorite groups, which are the fossil groups. And the talk is about Beyond the Gap, do galaxies care about group dynamics? Okay, Habib, right. Welcome.
Thank you very much. Well, thank you, Alfonso, for being a host here and also arranging this talk during this short visit. The last talk I gave here 4 years ago was Mining the Gap, and it was the understanding of the galaxy formation. Now, I titled Beyond the Gap, so that's just to give you the impression that we have done some work in the past 4 years, and I will present what we have done lately. Okay, so I should thank my collaborators before giving the talk. I would like to thank Mushtaba Raouf, who happens to be here in his trip to La Palma for observing RAN. Amin Farhang and Halimeh Miraghaib, those are my students, postdocs later on, Qasem and Alexis Finoganov for the recent works that we are doing, and we have been collaborating with them for some years now. Ali Dariush in Cambridge, and Trevor Pondman, who just retired a year ago. Gary Mammon and Marina from IEP, who helped quite a lot to develop this concept, what I'm going to be talking about. Okay. Right. So the way I've organized this presentation is the following. Very briefly, I'm going to talk about galaxy groups, general, just to tell you what they are and what they are not, what to expect and what not. Then I will focus on properties of dynamically evolved groups, which is a name I often lately use for fossil groups for a reason that I will explain. And I will talk about their halo properties, IgM, and also halo evolution. Then I will at the end, focus on the galaxy properties and see whether group dynamics means something for the galaxies. So, and you go back and forth between the observations and simulations, because this is the whole thing we have developed. And of course, it wasn't us only. There were many other people who have worked on fossils, Alfonso and his group, and other people, which I will name during my talk. The whole idea of fossils and their importance or not has been developed going back and forth between observations and simulations, and you will see that throughout my talk. Right, galaxy groups. Now, galaxy groups are, it's not clear what they are actually, and I tell you why. Because, we know that only a small fraction of galaxies live in isolation. So most of the galaxies are part of galaxy groups and clusters. The case of galaxy clusters is less ambiguous because of the large overdensity. If you have a large overdensity of galaxies in particular part of the sky within a certain scale, then you end up having a collapsed system. At least in the core, galaxy clusters are collapsed. And what does that mean? So let's, forgetting about the dark energy, which doesn't directly concern the structure of clusters, the content of them is predominantly dark matter, hot gas, and the luminous matter, which are the bright galaxies, right? So these three components form galaxy clusters, right? If you do an optical survey, find these overdensities, you end up having a strong and bright X-ray source. Alternatively, if you do an X-ray survey and cross-match that with the optical, you will end up with such a large overdensity of galaxies, right? That doesn't happen in galaxy groups, though. Now, it might happen in some, but not all. So, for example, local group is a galaxy group. So, depends on what scale you look at the galaxies together and try to find the friends of friends, you might end up galaxy pairs to be a group, right? And also things like fossil groups, okay? Now, so there is a bit of a confusion what galaxies are. You can actually define galaxy groups based on whether they are collapsed system or non-collapsed systems. Well, that's pretty much the way I'm going to drive this. So about a year ago, we organized a meeting to honor the retirement of Trevor Pohnman. And I took some scientific rationals from that website that we put up. The meeting was at IAP. So the aim was to see whether, the big questions are whether galaxy groups are actually a scaled-down version of galaxy clusters. That's one theme of research in galaxy groups. Then the other thing is, how well do we know the selection function of galaxy groups, right? There are different types of galaxy groups. For example, you could have galaxy groups aligned in a filament, right? So basically, there are few galaxies along the filament. Slight overdensity, you can assign it to be a galaxy group. But as I said, you can actually have galaxy groups as collapsed systems. Now, these mean different things. Now, you can both assign velocity dispersion to both these systems, right? So you could have a velocity dispersion of 300 kilometers a second just for this. Similarly to this. For this, it means something. It means virialization. For this, it doesn't mean much, right? So if you select galaxy groups on the basis of velocity dispersion, there's a good chance that you're just detecting spurious objects. You have to have some complementary way to suggest that this is a collapsed system, right? Now, there are other questions. For example, how are galaxy groups influenced by their outer filamentary environment or not? And there are all sorts of questions which I'll try to basically answer. Questions related to compact groups, their relation to the dynamically old groups, the conversion of compacts to fossils, and also basically talk about the scaling relations and whether these scaling relations are actually affected by luminosity gap. Now, back to the issue of dynamically old groups. Trevor Pohnman, in a paper, Nature paper in '94, found a system which was the following. So he found a galaxy group which was dominated by a giant elliptical galaxy and with a huge X-ray, extended X-ray emission. Now, if you want to form such a galaxy within a group, you have to allow a good time for galaxies within a group to merge to form a giant elliptical galaxy. That means you have to wait 3-4 gigayears for these galaxies to lose angular momentum to the halo and merge and form this giant elliptical galaxy. And if you do that, if you allow such a time, if you observe such systems, it also indicates that these groups have had early formation epoch compared to general population of galaxy groups. Most of the galaxy groups that you observe are in this form. But there are this fraction of them, about 10-20%, that are turned into these systems. Now, the giant elliptical galaxy sits at the middle of this huge X-ray emission, which means a lot. Actually, it means dynamical relaxation for the group. So if you want to identify these systems, Jones et al. Introduced a quantitative way. They suggested to look for galaxy groups with a large luminosity gap between the brightest and between the brightest member and the second brightest member. So if you, of course, allow these galaxies to merge, you will create a luminosity gap in the system. And so that's one way of identifying it. But then you also have to have a large extended X-ray emission, at least 10 to 40 x per second. And that 10 to 42 ergs per second comes from the fact that every elliptical galaxy will have some X-ray emission due to its supernova activities and star formation. But the X-ray you're observing here is beyond that. It's about the IgM. So these two criteria, the first one on the luminosity gap will indicate that galaxies have merged in a group and formed this giant elliptical galaxy. And this extended X-ray emission with this at least 10 to 42 x per second, give or take, because you have to consider the Hubble constant as well, will allow you to find such systems. So, and the argument in this paper is that it is likely that compact groups will turn into fossils given them enough time. And this was motivated by the simulations, dark matter simulations at the time in 1980s. So if you identify such systems, then you can do a lot. And here, of course, I have to point out that luminosity gap alone doesn't help you. Because if you look at the Milky Way and the dwarfs around it, there's a large luminosity gap between the Milky Way and the Large Magellanic Cloud, right? Certainly more than 2 magnitudes. But that doesn't count as fossil. Why? Because this is not a collapsed system, right? Milky Way is not produced as a result of merger. It's just there, like every other spiral galaxy, right? So we have to be careful how to use these quantitative measures to identify galaxy group, what we call dynamically old galaxy groups or fossil groups. Okay. Now moving on, if you have now they have to do a little bit cartoon here. So now you have a collapsed halo, dark matter halo filled with hot gas. That hot gas will cool, right? Naturally, it will. It can cool catastrophically to go to 0 temperature by emitting X-ray. We know that there are heating sources that stops that cooling to be so catastrophic. That heating sources could be AGN, could be star formation, could be supernova activities of the central galaxy or other galaxies. So at the end, you will end up with a kind of a virialized system, the balanced system in which the heating and cooling are balanced, and also the dark matter will hold the hot gas. Now this is very simple system. If you find such a system, dynamically old system, then what you can do, you can look at the halo concentration, you can look at the halo morphology, the dark matter morphology, and I already indicated that the halos of these systems are quite symmetric. You can also look at the hot gas, its temperature profile, metallicity, cooling flow, and cool cores and non-cool cores, etc. You can also look at the galaxy properties. I have to also point out, you will say, okay, you know, why you're interested in dynamically old groups? Because dynamically old groups will retain information from the early universe. In the hierarchical structure formation, you expect galaxy groups to merge and form galaxy clusters. That's the way it goes. So most of the galaxy groups that we observe today are not old systems, they are new systems, right? They just didn't have the chance to merge with clusters. Now, if you find an old galaxy group, it has much more information than your general population of galaxy groups today. And what I'm going to tell you is that, yes, actually they are different systems. I have to also point out that we have to study this in a cosmological context. So you can focus and do a case study of these fossil groups or dynamically old groups, but generally what we will do is to study them in the cosmological context. Now the first thing to look at is the halo concentration. In 2007 I did a sample of fossil groups which are identified here, and reported a very high concentration for NGC 6482. This is NGC 6482. It's a giant elliptical galaxy with extended X-ray emission and nothing else. And the rest are just very dwarf galaxies around them, okay? Or this one, which was the RG 1416. This has a huge X-ray emission. This is a Chandra data. This is XMM data. It's huge. It's 1 megaparsec. X-ray around one single galaxy, and the rest are just tiny galaxies, right? So this is interesting, and what we found is that the halo is more constant. Now, how do we probe the halo concentration? Is by C200, which is the virial radius divided by the break radius if you fit FW profile. Okay, this is how it's been formulated. And they are more concentrated. That's an indication that these halos are formed early. Remember, at the time, we didn't have a cosmological simulation to see that these halos are more concentrated. All we had was the X-ray data. Recently, Butte reported, he did several, there were some extra analysis on this system. Eventually, they came up with a concentration of about 35 or so. And this is 6 sigma about the general trend that are expected from simulations. Okay, so this is a high concentration, most highest concentrated halo ever reported. It's actually reported by NASA annual report in 2005. Moving on, let's look at the hot gas properties, the temperature of the intergalactic medium. And of course, we have to look at the temperature for a given halo mass. The fossils or dynamically old groups are hotter in general, these red ones. It's compiled by Gene. Are hotter for a given halo mass. This is the M500. That's almost the core of the galaxy groups. If you look at the entropy at 0.1 R200, again, the core of the galaxy groups and clusters, you realize that fossils are closer to the self-similar scaling. Now, self-similarity is when all the physics of the system is driven by gravity, right? And usually the galaxy clusters are self-similar. But when you run into the group regime, heating and baryon physics takes over and gives you such a dispersion in the entropy. Whereas for the fossils, as we expect, they're dynamically old, they're more similar to the core of clusters. They fall along the self-similar relation. You can also look at the temperature profile. Now, one big issue in galaxy clusters, it's not an issue, but it's a phenomenon, it's the cooling flow, which means that when the gas compresses, it falls towards the center, it cools, it emits X-ray, but that means that it cools again and again catastrophically to zero. The zero temperature has never been observed, so there has been some lifting up of the temperature, but it actually goes down, right? So most of the galaxy clusters will have a turning down temperature like this. Fossils that we observed initially never showed any cool core, what today is called cool core, like these two. But there is a discrepancy. I mean, there is a. It's not like every fossil will look like this. Some fossils do show a drop in the temperature, but some fossils don't. Right. So there is a mixed bag here. Okay. Well, that's important. So we have to see why there is this difference. Now, that was up to 2007, when we didn't have cosmological simulations. When the Millennium cosmological simulation in large volume became available, then what we did is that we started to basically trace back the evolution of this fossil group. So we identified fossil groups in the simulations at redshift of 0, as we do in the observation, based on luminosity gap, X-ray emission, and so on. And we look at their mass evolution. So this is the mass evolution. At redshift of about 0.7, fossils or dynamically old system acquire 65% of their final mass. Whereas the young groups, and now you can define a young group which has a very small luminosity gap, they have acquired only 45 or 50% of their final mass, which means that their seed or the progenitors are more massive in the past. So this is just an example of evolution of a fossil system against a control system or very young galaxy group or evolving system. At redshift of 1, the core is already present, so it goes through a very small, slow growths between these past 7-8 gigayears, whereas for a control system, it's nothing there. Basically, the group assembles very close to redshift of 0. So that's basically what it says. Now, of course, other people are also... The first person to actually report such an evolution was the Ongia, who collaborates with Alfonso. And they are now, of course, recently they have published a new work which looks at this in the hydrodynamic simulations, and we are discussing the consistency of the results and figuring out what each other are doing, each of the two groups are doing. Now, a lot of people have taken luminosity gap for granted, in the sense that if the galaxy group has a large luminosity gap, it's an evolved system, and it's early form system. These cosmological simulations allow us to actually probe this. Now, what we do is that we color code the mass evolution of galaxy groups here. And this is the luminosity gap threshold of 2. You see that if you only take luminosity gap, the chance that you will find an old galaxy group, an early formed galaxy group, will be 61%, against 6% of the young. And that depends very much on the luminosity of the central galaxy. If the central galaxy is very luminous, the old group will reduce to 22%, against 26% young system. What this means is that the luminosity gap alone is not a very good indicator of the age of the system. So there's much more to age of a halo than just the luminosity gap. So we call it age dating galaxy groups. Age dating galaxies. So in the real universe, you cannot assign an age to a galaxy system. This is what we want to do based on the information we acquire from the simulations. So we have to rely on two other parameters. That's the halo concentration or the decentering. Decentering means the central galaxy, how a central galaxy is separated from the center of the halo, exactly as the Poneman introduced in the first fossil system. Now, an old galaxy group will have higher concentration, again, in comparison to the young ones, right? And this is across the halo mass. An old group will have the central, the dominant galaxy closer to the center of the halo. Young ones will have it separated, right? So that's the additional information you look at. So if you want to basically identify a dynamically old system, you have to go beyond the luminosity gap. You have to take either this or both, in principle, into account. Now, observationally, this is quite difficult because you require deep X-ray observations in order to model the halo concentration, whereas this is very easy to, it's very economic to obtain. So you can always, even with optical data, you can assign a centroid to galaxies and then check how far is the brightest group from that centroid. That's what we do. Right. The other question was asked in that 94 paper, Nature paper, was whether the suggestion that compact galaxy group turn into fossils, given enough time. In fact, we checked this recently. 20 to 34% of fossil galaxy group between redshift of 0 and 1 have passed through this compact phase. Now, this compact phase that I talk about is the Hickson compact group phase, which is very restricted. You have to have 4 galaxies of difference of 3 magnitude from the central galaxy, and then you have to have a ring that there isn't any bright galaxy. So it's very, it's not ordinary. You have to pick specific groups to meet this Hickson compact group criteria. So there might be other form of compactness that fossils could have experienced during their lifetime. Yes, so in principle, yes, you can turn turn compact groups of different forms into fossils, and that's what is happening actually. Right? I won't go into much detail because I don't have much time. Then there were limited things we could do with the Millennium simulations because in general, galaxy properties in the early Millennium simulation were actually assigned semi-analytically, which means that there's no physical galaxy, there's no baryon, it's all computational. But with the help of illustrious simulations and other hydrodynamic simulation, like Eagles, we can actually do a bit more. Here, in the simulation, you actually have some galaxies physically there. Of course, you have to debate, whether these are exactly the same galaxies as we find in the observations, but that's the model improvement that is ongoing. So, one thing we couldn't do in the semi-analytic modeling was the hot gas temperature. So we had no clue what the hot gas temperature is. Or, for example, how the mass accretes into the central black hole of fossil galaxy groups or dynamically old groups. And this is what we do in the hydrodynamic simulation. So this is the temperature profile. I showed you the observed temperature profile for NGC 6482. In the simulations, as you see, the old galaxy groups have their temperature lifted up all the way, right? So they're hotter in general. It's not like they're hotter in the core or at the skirt, they're systematically lifted up, right? And if you do the mass temperature relation, just similar to this one, you realize that again, that the hot gas temperature of dynamically old systems are lifted up against the young ones. So that's reassuring. Then the question comes, what did the central galaxy experience during this 7 gigayears of evolution? What happened to the central galaxy? Now, central galaxy is very special in galaxy groups and clusters. Whatever happens in the halo, that central galaxy will have some kick of it, because everything will sink into the center, it's in the bottom of the potential veil, and so on and so forth. That might include the AGN activity, supermassive black hole, the stellar population, and everything. So what I show here is the probability of the mergers. When did the mergers occur? The central galaxy mergers occur. So we show that there is statistically a 2 gigayears difference in the episode of the mergers of the central galaxy in young groups and old groups. So the old ones have their mergers, most of their mergers in the past, and the difference is about 2 gigayears. But 2 gigayears, does it mean something for the central galaxy? Can we observe this difference somehow? Is there any star formation indicator or AGN activity indicator that gives us the clue that this 2 gigayears was actually something that happened? Now, this has been going on for some time now, and I would like to refer to the work of the Barbara, which I remember somebody from IAC was also involved in this research, but I can't say who. So what they did is that they looked at the central BGG of the fossils, some field galaxies, and also the dominant galaxy or the brightest galaxy of compact groups. And what they found, and I think I like to actually draw some lines to guide your eyes, is that it appears that the age assigned to the stellar population of the central galaxies in compact groups is actually older than the one assigned to the fossil central galaxies. I think they follow the general trend of the metallicity and the alpha enhancement, but this is pretty impressive. Their conclusion in the paper was not very promising in a way. They basically casted doubt that if the fossils are old system, why should their central galaxies be so young? Or I think that was the kind of the impression I got. And I think that's fine. We know that the central galaxies of the fossil groups are merger products. And if you had a mergers like 3-4 gigayears ago, that will lower the age of the global age of the stellar population down anyway. Unless you do stellar population decomposition, And then you assign old and young age to different parts of the galaxy, which nobody has tried, right? So that's something to think about. I should actually because this is presented in the paper, I couldn't basically stop thinking that this is the location, the crosses are the location of the central galaxies. And these are the X-ray emission contours from all the Sky Rosat survey. We know that it's a shallow survey, it's the old time. But I think it's very important we pay attention to the fact that these BGGs should be at the center of the halo. And if they are not, we are probably not dealing with the fossil, as I tried to explain today, that it's not all about luminosity gap. We know that the luminosity gap of all these systems are high or large, but the central galaxy in some of them doesn't appear to be coinciding with the center peak of the X-ray emission. That is something to look at, maybe revisit this subject. Other people also have went and observed fossil central galaxies with Hubble telescope. This particular study was focused on the population of globular clusters. And so they were asking the question, if they are different systems, how would their globular cluster look like in terms of the color bimodality or metallicity bimodality and so on? And I'm not an expert on this, so I just wanted to basically appreciate that they have done this study, which I think what they found is that actually their color, red color, is too red, basically, especially for this system. But I don't know in principle what is the debate now on, and what does all this color bimodality of globular cluster links to the merger history of their papers that try to link this to merger history of elliptical galaxies. But they are not that different from M87 or generally Virgo cluster globular cluster populations. What they point out is that they see a signs of mergers, past mergers, in the central galaxy. Well, that's a very good thing. Although, again, they think this is not a good thing to observe, but yes, we know that the central galaxies of fossil groups are merger products. And all three show the signs of a merger at the core. Again, the question that one could ask is, how is that core of this central galaxy is rotating against the globe, the bulk of the galaxy? Do they have like counter-rotating cores, or do they have core-rotating cores? These are interesting questions to basically look at. Right, I'm moving on. What we did recently, well, Trevisan kindly did it, and she went through all the technical troubles of doing this work, which is very much appreciated. So she looked at the stellar population of the central galaxy and not only the central dominant galaxy, but also the second brightest galaxy, and try to see whether the luminosity gap is giving any indication that something is different. And if you look at the color or specific star formation, alpha enhancement or anything, there doesn't seem to be any correlation between the luminosity gap and the stellar population of these galaxies. Okay, here in this work, she did not consider these BGGs to be at the center of the galaxy group, though. Okay, so the conclusion so far on the stellar population is that there isn't much difference between the stellar population of the dominant central galaxy in dynamically all groups with the rest of the population of giant elliptical galaxies. Okay. Now, let's move on to the AGN activities. Now we have this very simple halo. The fossil central galaxy forms. The gas cools to the center. Then the central galaxy AGN ignites and starts some emitting radio and other wavelengths, but we are mostly considering radioactivity here, and that mechanically heats up the core. Now there are other heating mechanism, but let's look at the AGN only. And maybe I should just use this galaxy formation factory diagram. Again, repeating the same, the hot gas cools into cold gas, stars form, hot gas also cools directly into the central supermassive black hole. Central supermassive black hole heats up the gas, stars, and everything. So this is the cycle that we go through. Now, this is for an isolated galaxy group. If you have a merger, if two groups merge, then things will get nasty. And for example, the cold gas, the flow of the cold gas into the supermassive black hole will be blocked, or it will be enhanced, because there will be galaxy mergers, and that will lead the cold gas into the central black hole. And also the hot mode accretion will also be affected, such as coma cluster. Coma cluster doesn't have that the cool flow or cooling flow. So the X-ray peak is very shallow, simply because it's a merger product of two galaxy groups or clusters. Now, being motivated by that simple cartoon, we said, okay, let's go and observe the central galaxies of fossil groups with radio, and in two different wavelengths, 1.4 gigahertz, which is the recent AGN activity, probes the recent AGN activities, and in longer wavelengths, like 610 or 325 megahertz, which is the cooler electrons. So that is the past AGN activities, okay? So we observed fossils which are presented as the power of 610, power of 1.4 gigahertz, and we compared it to some normal BGGs that we found in the literature. And they appear to be presenting lower radio as compared to the other bulk of the other systems. So this is the radio emission from one of the systems, and these are the others. So this was very exciting. So we said, okay, now this is a small sample, let's expand the sample. And we found that the gamma survey was suitable, simply because it went deeper. And you have to go deeper. Fossils are nearby systems, that's fine. But because you want to probe this luminosity gap, you have to go a bit deeper to be form a complete sample. And gamma was convenient to use. We have actually done with SDSS as well, so that's the same results, but okay, so this is presented in gamma. So these are all the BG galaxies in gamma survey. These are the BGGs, and we have from the BGGs, we identify two samples of old and young groups. These are how they're distributed in redshift. This is how we define old and young systems. So magnitude of -22 or above, or brighter. Luminosity gap for the old one is 1.7, but the galaxy must be within 100 kiloparsecs of the centroid of the group. For the young ones, it's exactly the same. Luminosity gap is very small, and the central galaxy must be outside the central 100 kiloparsecs of the centroid of the galaxy group, just to say that the group is evolving, basically. So this has been done, and again, so the sample then was matched with the VLA first survey, and there you see, no smoking. It means that the luminosity at 1.4 gigahertz, radioluminosity, is lower by about an order of magnitude compared to the BGGs in the evolving systems, right? Exactly as we've observed at the GMRT in the previous plot, right? So this is the GMRT observation, our own observations. These are from the gamma and the VLA. So we took both the integrated flux and the peak flux, and why we did it, because there is a possible source confusion issue, and we try to eliminate all the source confusion, because if the evolving group have too many galaxies, bright galaxies, you might mix up the radioluminosity, but we ensured that the separation of the galaxies from each other is at least 3 times the PS, or the beam size of the radio survey. So just to ensure that there's no source confusion. Now this is for the relaxed and unrelaxed, or old and young groups, which take into account luminosity gap as well as the off-centering from the center of the group. Whereas this one is for fossils and non-fossils, pretty mixed up. So if you take only luminosity gap, you're not going to find much of a difference in the AGN activities, right? So why did us find this large gap only looking at the fossils? Simply because these fossils inherently not only had the large luminosity gap, but the BGG was right at the center of the group. It's implicit criteria in the old fossil samples. But if you only form a new sample based on luminosity gap, things might get washed out. So that's very important. That's how I say going beyond the luminosity gap. Now, in the gamma database, there is also a limited radio observation 3.325 megahertz, which is also quite useful. But of course, it's limited. So most of it is non-detection. So you can put an upper limit on the radio power, and these are the upper limit. Again, if you compare, if you take this overlapping region, you realize that this must be all lower. Therefore, there is a substantial difference in the radioactive. But it's very important to go and do this observation deeper with radio, because we want to see how far it goes down. And that basically tells you when was the last AGN activity, because this spectral indices of the radio emission will tell you the age of the past AGN activities, okay? Now that we did this exciting observations, we said, okay, fine. Can cosmological simulations reproduce this? Now that was another big effort. So we have to go and, because there is no semi-analytic model that would give you such a measure of radio luminosity. So Mujtaba had to work with an expert on semi-analytic modeling, Darren Croton, and tweak his semi-analytic model, implement new jet physics and cocoon enlargement and heating and so on. And he had to compare all his results with whatever it's in the literature in order to come to this plot. So again, the bold data points are the observed data points, and everything on the background is actually from cosmological simulations. And you see the consistency in the results. Again, the BGG radio emission in the simulations is also for young systems is higher or more powerful than for the BGGs in the old systems. So that was a success. So then we started from observations, moving to simulation, understood a bit of, then moving to observations, and now ended with another set of simulations. So that's almost it. I just do 1 or 2 slides. I just want to advertise the new work that we are doing. Alexis and Qasem have compiled a larger sample of galaxy groups from XM, CFHT, Cosmos, and Aegis. And we are able to actually push this group sample into redshift of 1.3. All the studies we did actually were all limited to local universe. Now with this sample, we will be able to actually push this into, then we will be able to actually look at the young systems at higher redshift, compare it with the old systems at lower redshift. That will be interesting. Already we published 2 papers on the, this is nothing to do with the fossils or dynamically old systems. This is general population of galaxy groups. So we will move on to fossils later on. This is just the general, and we find like star-forming BGGs. This is the very small stellar mass, actively star-forming BGGs we have found, and these are all being reported in the papers. So that was just to highlight the work. So, conclusion. We did observations to probe the halo concentration. We found them quite high. Hot IgM we have found, but still this is debated. Scaling relations have been reported. About 30% of the compacts turn into fossils. Simulations we studied the hot IgM and their properties compared with observations. We found that the supermassive black hole of these fossil central galaxies are more massive than the non-fossils, but their accretion rate is lower. That is from the hydrodynamic simulations. Going back to the question whether the central galaxy or some galaxies actually understand the dynamics of the groups, there is a mixed feeling. There are some evidences from the AGN activities that they actually do feel the dynamics. There are also some morphological distinctions, but I didn't talk about it. Some people say no, or we also agree, actually, to the extent we have done the analysis, that the stellar population don't care about the dynamics. And also the distribution of globular cluster doesn't seem to care much, right? Samples are small, analysis methods are probably not adequate, perhaps. So we need to enlarge the sample, improve sample selection. Just don't take luminosity gap for granted that it will give you all groups, it won't. And we need improved analysis techniques. Okay, so that was my conclusion. And in 1 second, I will only show you this project we are involved in. That's the 3.4 meter telescope for the Iranian National Observatory, which is just past the detailed design, September last year. And we are in the phase of construction. Already the construction at the site, the road and everything has started. So if you want information on this, you can go to the website, or if you have any questions, please let me know. Thank you very much.
Thank you very much for this very interesting talk. Questions?
You say that there is some similarity in some sense of an isolated galaxy, a massive galaxy, and a group. If you live some time, this group will become a galaxy. Do you think it's possible to make a sort of a scaling relation, including groups and galaxies, and taking parameters like the mass of all the group and the galaxies, and they will fit into a scaling relation?
Yeah, okay. So there is one has to be very clear about what sort of isolation we're talking about. Because in the groups in collapsed groups, the central galaxy will be an giant elliptical galaxy. That's pretty much universal, right? If it's not, I would strongly say that it's not a collapsed group, okay? Now, if you compare it with an isolated galaxy, that isolated galaxy, if it's a giant elliptical galaxy, it's in a group. If you don't see the group, it means that you're not looking hard enough, because there's no way one can produce a luminous elliptical galaxies in isolated universe. It's simply not possible. At least the simulations don't allow it. In the observations, nobody has. The fossil groups, some suggested that fossil groups are luminous isolated elliptical galaxies. But how isolated? If you look at slightly deep enough, there will be a lot of dwarf galaxies around them. There will be an extended X-ray emission. So in principle, what I'm saying is that there is no isolated galaxy of giant elliptical.
But if you leave enough time to a fossil group, it will become a...
No, the problem is that the dwarf galaxies will take more than Hubble time to merge with the central galaxy, because the dynamical friction time scale is very large. So in principle, the L-star galaxies, the typical galaxies, will merge in few gigayears, but all the dwarf galaxies will stay because they take forever to merge.
Couldn't the hotter IgM of the older fossil group be explained by their lower density, lower IgM density? Could we explain this?
Well, sorry, I went in the wrong direction. So I think in principle, well, not really. I mean, the density, the old galaxy groups are X-ray luminous, right? In principle, or I have to revise that. I say there is the LT relation, which is the temperature X-ray luminosity relation. There is no difference between an old and young group in that scaling relation. They are the same. Which means that whatever has lifted up the temperature has also lifted up the luminosity, yes. Right? And it is easy to argue that this is because of the early formation epoch of these galaxies. When these fossils are formed, our argument is that the universe was hotter and more denser. So if you form a galaxy group at high redshift, its core should naturally be denser and hotter, right? So there is no such a thing as, these are hotter, but so the density are more shallower or lower. No, it's not the case.
So beyond the gap, yes.
Beyond the gap.
As you know, I am very skeptical also about the gap.
No.
Just select only old system with the magnitude gap. This is not telling us nothing. So, okay. What is the future for you? How we have to select the new samples, new large samples, using simulation? What is the future?
In the simulations, it's very easy because we have the mass evolution. So we don't have to rely on anything, basically. No luminosity gap, no displacement, or nothing. So it's very simple. The problem is with the observations. Now, in the observations, I would strongly go for, and I will never, ever go back to luminosity gap alone, unless it is intrinsically somewhere there is the central galaxy sitting in the X-ray emission and so on. If we have an X-ray emission, the BGG must be at the center. If not, take the group centroid and take the BGG as close as possible to the center of if you want to find the old ones. If you have some means of halo concentration, that's even better, but that's very hard to get. So if I want to do a sample selection observationally, I would definitely go back to the drawing board, and that drawing board is exactly what Trevor Perlman and others did in the first place, which is this. Whatever they selected, the central galaxy was at the peak of the X-ray. They didn't say that, but it was, right? So always do that, and I think that's the right thing to do. To be honest, I'm very open-minded. I don't know how much of the central galaxy really feels this group dynamics. AGN appears to be, getting this feel. That's fine. Stellar population. If I want to focus my research on this continue, I will say definitely go for IFU. Definitely go for improve the stellar population modeling. Try to see if there is something there. This single stellar population model doesn't seem to be giving anything. But then also, I think the work that Lebaber did with someone from here, I know the paper was involved at the time, it was 2008, interpret this in the light of understanding that central galaxies are actually merger products. And I saw this interesting age difference between fossils and the compact roof-bright galaxies. I think that means probably is telling us something, so one has to check that.
Further questions? Otherwise, let's thank the speaker again, and then we can join to the scientific coffee.